let's just dive right into this ultimate exam review explainer where we're going to break down the fundamental physics of forces so you can absolutely ace your upcoming test. If you've been staring at your textbook and feeling, a bit lost, don't worry, you are in exactly the right place.
Look, I completely get it. Studying physics can feel super overwhelming. But stick with me. I'm going to be your tutor today, and we're going to turn all these tricky concepts into guaranteed points on your exam. I honestly love breaking this subject down, because once you actually see how forces work in the real world, it all just clicks. So grab a notebook, get comfortable, and let's conquer this thing together.
Here's our game plan for today's explainer. We've got 4 main topics to tackle. First, the basics of pushes and pulls. Then, contact forces in action. Third, those invisible non-contact forces. And finally, weight, mass, and buoyancy.
All right, let's kick things off with Section 1, Basics, Pushes and Pulls. Think about Sonali and Ragini from your textbook out riding their bikes. Imagine it's a super windy day, and the wind is literally pushing back right against them. To keep moving forward, what do they have to do? They had to push their pedals way harder just to fight against that wind. That is a perfect, everyday example of forces at play. They're exerting a push on those pedals to counter the push of the wind.
So the bottom line is that a force is simply a push or a pull. Imagine trying to move a giant, heavy cardboard box. You can push it, you can pull it, or you can lift it, which is, essentially just pulling it up. But notice the key detail here. You have to actually interact with that box. A force only happens when 2 objects interact. Oh, and for the exam, definitely don't forget the units. Force is measured in newtons, represented by a capital N. And the second that interaction between the 2 objects stops, boom, the force is gone.
Okay, before we move on, quick pop quiz. You'll probably see something like this on the test. If literally no one stops a rolling ball, why does it eventually stop moving on its own? I mean, it looks like no force is acting on it, right? But remember, we just established that a force is completely required to change an object's speed.
To figure out what's going on there, let's jump to Section 2, Contact Forces in Action. Let's uncover what's secretly slowing that ball down.
The culprit? Friction. And what's really fascinating is how friction actually works on a microscopic level. Even a surface that looks perfectly, totally smooth to us actually has a huge number of tiny microscopic irregularities. When 2 surfaces touch, those invisible little bumps basically lock into each other like a jagged puzzle. They actively fight against any effort to move one surface over the other. Because the ball and the ground are physically touching, friction is what we call a contact force. And remember this, it always acts in the exact opposite direction of the motion. Now, you'll definitely need to be able to spot examples of contact forces on your exam. A big one is muscular force. But don't get tricked. Muscular force isn't just, lifting heavy weights at the gym. Your textbook specifically points out that it's also your heart muscles contracting to pump your blood and your jaw muscles chewing food to push it down. Also, keep in mind that friction doesn't just happen on solid ground. Air and water totally exert frictional forces too. That is exactly why airplanes and ships are designed with those really specific, sleek, streamlined shapes. It's just to reduce that drag.
All right, let's flip the script and look at Section 3, Invisible, Non-Contact Forces.
You will for sure be asked to compare these 2 concepts on the test, so let's break it down. Contact forces, like we just talked about with friction and muscular force, absolutely require physical touch. No touching, no force. Non-contact forces, though, they operate completely at a distance. Think about magnets. They can push or pull each other without ever making physical contact. And the Earth continuously pulls objects down via gravity without any physical strings attached.
Another highly testable example of a non-contact force is electrostatic force. Have you ever vigorously rubbed a plastic scale or maybe a straw with a piece of polythene? When you do that, electrical charges, static charges, build up right on the surface. If you hover that charged scale over some tiny uncharged pieces of paper on your desk, it'll instantly snap them up. The paper literally jumps to the scale without the scale ever touching the desk. That invisible, magic-like pull, that is the electrostatic force in action. Okay, lean in for this one, because teachers absolutely love to throw this trap question on exams. Are mass and weight the exact same thing? In everyday casual conversation, yeah, we totally use them interchangeably. But in science class, mixing them up will definitely cost you points. Let's clear that up once and for all in our final section, weight, mass, and buoyancy. Here is the golden rule you have to memorize. Mass is, it's the actual amount of physical matter in an object. It's measured in kilograms or grams, and it absolutely never changes, no matter where you are in the entire universe.
Weight, however, is a force. Specifically, it's the Earth's gravitational pull on that object. Because it's a force, weight is measured in newtons. And here's the kicker. Because gravity changes depending on where you are, your weight actually varies by location.
Let's put that into perspective. If you have an object with a mass of 1 kilogram, it weighs about 10 newtons right here on Earth. But let's say you took that exact same 1 kilogram object to the moon. Its mass, still exactly 1 kilogram. But its weight, it drops to a mere 1.6 newtons. Why? Because the moon is way smaller, so its gravitational pull is much weaker. So remember, mass is constant matter, weight is a localized pull.
Now, what about when things get wet? What happens to weight in water? Have you ever noticed that if you dunk a heavy plastic mug into a bucket of water, it suddenly feels, like, weirdly lighter? That's Archimedes' principle at work. The water is actually pushing back up against the mug. This upward force applied by the liquid is called the buoyant force, sometimes called upthrust. So, figuring out whether something is going to sink or float, it's literally just a vertical tug of war. You've got the Earth's gravitational force pulling the object downward. That's its weight. And at the exact same time, you've got the liquid's buoyant force pushing it upward. If the downward pull is stronger, the object sinks straight to the bottom. But if the upward buoyant force equals the object's weight, boom, the object floats. And here's a wild little fact straight from your textbook to help this stick. Usually, we think of rocks as super heavy things that just sink like a stone, right? But pumice is a solid volcanic rock that actually floats. See, during a volcanic eruption, lava sometimes cools so incredibly fast that it traps tiny bubbles of gas right inside it. This creates a really porous rock filled with air pockets. Because of all that trapped air, the overall rock is actually less dense than water. That means the upward buoyant force can easily match its downward weight, allowing a literal solid rock to float. How cool is that?
All right, let's wrap this up with a quick cheat sheet for this explainer. If you want to guarantee a great grade, lock in these 5 golden rules. Number 1, a force is a push or pull, measured in newtons. Number 2, forces only exist when objects interact. Number 3, know your contact forces like friction versus your non-contact forces like gravity and static electricity. Number 4, mass is constant matter, but weight is a force that completely changes based on gravity. And number 5, sinking or floating is just a battle between downward weight and upward buoyant force.
To test your new physics mastery, I'm going to leave you with this final thought straight from your end of chapter exercises. Based on everything we just learned about those microscopic irregularities that cause friction, how would you alter a totally smooth horizontal floor to force a rolling ball to come to a stop much, much faster? Think about what you could do to increase that contact force. Keep pondering that, keep reviewing those notes, and you are going to absolutely crush this science exam. You've got this.